Hello, my name is Brent Ruttle, and in my project, I'm working with time series data, and more specifically, the DARTS Python library. I also introduced attention temporal convolutional networks. So the DARTS library is pretty useful. It has a nice API. It's similar to scikit-learn, but it's more tailored toward time series data. So you've got all kinds of nice functions and methods for working with time series. Whether it's univariate, multivariate data, hierarchical, working with covariates. So it has all that kind of stuff. And then it has all of these features here. It has a lot of built-in data sets. So if you want to get off the ground and running quickly and understand how to use darts, those data sets can be useful for that. And then it has all the different things that you would see in a scikit-learn type of library. Building pipelines, transformations, that kind of thing. Another thing DARTS has is a lot of built-in models. One of its drawbacks, however, is that it does not have the ability to insert a custom PyTorch model, which I was hoping to be able to do with the ATCN, but was not able to pull that off. But it does have a lot of nice models and advanced models if you want to do some benchmarking or maybe just use them in your own research. It also has some nice features for anomaly detection, so it'll take some of those built-in models and it'll wrap some scores with it, so you'll be able to detect anomalies using some kind of ground truth. So that's a really nice feature, and it's pretty unique to DARTS. So ATCNs, I'll let you read this problem statement. Just hit pause. But here's the network architecture. Basically what we're doing there is using a GAT, breaking it off into two graphs. You've got one to tease out temporal relations, the other for variable relations. Then we feed that into a temporal convolutional network. This is kind of a change from the state of the art. Most networks are using something like an LSTM, but TCNs are actually have a lot of promise because they're a lot less costly in terms of computational power. So when I get in, and here this just kind of breaks it down a little more. This slide here, you can pause and read that. So results here, this is what you would typically see if you're looking at an anomaly model. You've got the anomaly score up top, some threshold to where you say whether or not there's an anomaly, and then you've got the ground truth on the bottom. Interestingly, with this run, I was not able to repeat the paper's performance. So unfortunately, the performance I got was basically mediocre for the state of the art. So I'm not sure if that was a function of me having to do some customization to get it to run, or maybe just some random error. But that was something interesting that I learned. So that's all I have. I hope you enjoy the project.